Welcome to this webinar on how to do semantic search with BERT, explained along a real case study. My name is Jona Welsch and I'm a machine learning scientist at DIDA. Before we start with the webinar, I would like to introduce DIDA a little bit to you. DIDA has an experienced team of machine learning scientists, and we implement machine learning projects in multiple areas. Our main focus here is on computer vision and natural language processing, where computer vision focuses on the processing of and reasoning from images and videos, and natural language processing, as the name says, is about the reasoning from natural language, especially from free-form text in our case. For both of these fields, I added a few links leading to case studies, use cases, and blog articles from DIDA about these two fields. During the course of this webinar, I will give an introduction into what semantic search is. I will present the concrete case, which is called industry codes, along which I will show how to use BERT for semantic search in practice. I will give a quick introduction to BERT and its architecture, as well as how to train BERT for the concrete task of semantic search. And in the end, I will give a quick overview about the project procedure used for the industry codes case and the results we reached there. So what is semantic search? Semantic search can be seen as a subform of text search, and the goal of every text search is to provide the most suitable data points for a query. So the usual setup is that we have some kind of search request and a database or document collection to be searched. Both these things go into an algorithm as an input, and this algorithm then delivers a search result, which is usually a ranked result, meaning that it returns different results ranked by their probability that they actually fit the original search request. And applications of semantic search are, for example, document retrieval or internet search engines. So, for example, if you enter a query into Google, most likely some part of the algorithm going on in the background will be based on semantic search. The word subform already tells us that semantic search is not the only way to do text search, so let's put it a little bit into perspective. For explanation purposes, one could split up different text search methods into 3 categories, although they are not mutually exclusive. Starting with full text search, we are very much on the appearance-based scale of text search methods, and full text search would be really just looking for the exact word in your search query and trying to find it in a certain text section. An example for this could be substring matching. Then there would be statistical methods which try to somehow take into account the content of certain words. For example, one could weight different words according to their occurrence in a certain document. An example for this would be TF-IDF. And on the other end of this scale, so very content-based, would be semantic search with a full focus on the content using background knowledge and context. And an example for algorithms or methodologies using this would be ontologies or neural networks. As a side note, semantic search can also be done with images, for example, but here we focus on text, and if I say semantic search in the course of this webinar, I always mean semantic search on text. So if there are so many different ways to do text search, one could ask, why is semantic search so interesting? And the slightly exaggerated answer to that could be, non-semantic methods are fast, but do not understand. So non-semantic methods have a few advantages. They need usually very little computational effort, meaning that they are fast. They are usually based on understandable fixed rules, which means that their results are explainable. And quite often they also don't need any additional data to be deployed. Disadvantages are that they can only include context to a very limited extent. So they have difficulties with synonyms and homonyms, So if there are two words with the same meaning or a word which can have different meanings depending on the context, quite often non-semantic methods cannot identify these cases. And also, similar to that, they cannot deal with paraphraseations of certain expressions. There are a few ways to alleviate these problems, at least to some extent, but all of them are very manual and require quite a lot of time. Semantic search, on the other hand, focuses on the meaning, and its goal is to find search queries and database entries with similar content and not similar appearance. And the idea on how to achieve this is to include context and background knowledge. As I said just now, possible implementations of this are ontologies, which are manual and time-consuming, basically meaning that you draw a net based on words and their different relations to each other. And another option would be neural networks. They find these connections automatically, but need quite a lot of data to do that. The advantages of semantic search are therefore that the search intention can be better met of the user, and users need less knowledge about the search database. You don't need to know what the exact expression for something you're looking for is in the database. You just need to know what content you're looking for. Disadvantages are that semantic search is slower and it usually needs to be trained on data, so it doesn't work out of the box. So now that we know what semantic search is, we can look at our practical case study, which is called industry codes. So let me explain the problem to be solved first. When citizens want to register a business in Germany, they should specify something called an industry code. There are more than 800 different industry codes, and it's very hard to know which industry code is the correct one for your business. And to make it even harder, the descriptions of these industry codes are provided in the language of authorities, which is very different from colloquial language. To give you an example, when we would normally talk about a car, the corresponding expression used by German authorities would be something like motor vehicle with a gross weight of less than 3.5 tons. So you can see that finding the correct industry code for your business might take some time. Our client also wanted to make it possible to register your business online, but asking questions when you are unsure about which industry code to use is way harder when you first have to find the correct telephone number and reach someone in the responsible authority. The solution to this is to use semantic search with BERT, between colloquial business descriptions and the description of industry codes in authority language. Our desired output are then the top 5 industry codes, which are most likely to fit the business description. Before we explore how this can be achieved with BERT, let's see what this looked like in practice. The interface with which citizens should interact with the semantic search algorithm was an already existing chatbot from our client. Citizens who want to register a new business can enter a description of this business, for example, printing personalized fabric bags. The algorithm then does a semantic search in all industry code descriptions and outputs the most likely industry codes. What we see here are real results, but only the top 2 results for readability. The top one is actually the correct result, and you can see that none of the words used in the user's description appear in the industry codes. This means that our algorithm has actually understood the meaning of the user's input correctly. For example, it learned the connection between fabric bags and textiles and apparel from the data it has been trained on, although these are very different words. So now that we have seen what BERT can do, let us look at what exactly BERT is. And to understand that, we start again with some perspective. Most language processing methods follow a similar scheme. All start with some kind of preprocessing, which includes methods like tokenization or initial embedding. And one could describe this step with from text to numbers. The next step is the actual language processing model, which often does some mathematical calculations on vectors. This step could be described as using connections between numbers. And the last step is some kind of post-processing to generate scores or text as a result. This can be described as from numbers to statements. BERT belongs to the model section, so today we will focus on this part and, for example, assume that some initial embedding has been calculated already, meaning that we already have some way to represent text as numbers. The basic idea behind a lot of neural networks used for natural language processing is to learn an assignment between text and some space, so that entries with similar content are close to each other in that space. In the simplest case, connections between words are learned. You can see a two-dimensional visualization of such an embedding on the right, and there are a few interesting things in there. For example, man and woman are pretty close to each other, being both humans. But what's also really interesting is that the difference, so the way from king to man, is completely the same as the way from queen to woman. So there is already some meaning in this embedding and the positioning different words have in regard to each other. Such a word-wise embedding can help with treating synonyms correctly, but homonyms, so one word with two meanings, are difficult. Because a word in this setting always has the same embedding, so the same location in this 2D space, independent of its context. There are a few freely available pre-trained implementations of single word embeddings such as word2vec, fast text, or glove, which are able to give you embeddings which are similar to what we see here. So some problems that non-semantic searches, such as synonyms, are solved by using single word embeddings, but others, such as homonyms or paraphraseations, are still not solved because they need context. And this is exactly the problem BERT wants to solve. BERT stands for bidirectional encoder representations from transformers and is able to learn relations between larger text units and not only words. It is a neural network which was published in 2018 by Google and builds on the so-called transformer architecture, as the name says, which we'll see in the next slide. It is used in the Google search, so whenever you enter a query in Google, the top 20 or 50 results are found by using other algorithms, but the ranking of these top results is done using BERT or a successor. BERT is able to be aware of the context of words in its calculation, and to be able to do that, it needs to be trained on huge amounts of data. The good news is that a big part of this training can be done unsupervised, meaning that freely available text data can be used for training. For example, the Wikipedia for any given language, which is a very large text corpus. So let's look at BERT's architecture. BERT actually uses only one part of the original transformer architecture, which you can see on the right, and this is called the encoder part. And this is what you can see now. The most important properties of this architecture are the use of skip connections, which allows to reuse earlier calculation results from within the model, some technique which is also used in other very well-known architectures such as ResNet. The next point is a technique called layer normalization, which leads to better generalization to unseen data, so data which was not in a training data set. And the most important part is something called self-attention, and I'll explain this in the next slide. Before we go to self-attention, let's look at the way data takes through the BERT encoder. Looking at the diagram, we see that we have some form of input embedding. So this is the pre-processing part not discussed today. Then there is an attention section, which is explained next, followed by a feed-forward section, which is more similar to a classical neural network. And then we have this NX on the left, which means that this whole process of attention and feed-forward network is repeated multiple times, and what we get out in the end is an embedding for my input words, which assigns words a position in space as we have seen before. So what does self-attention do? Self-attention enables words in a text to influence the embedding or meaning of other words in the text. This means it is context-aware, and we can see this in our example, which is actually a visualization of real computations in a trained BERT architecture. So we input the sentence, "The animal didn't cross the street because it was too tired." And to find out what the "it" in this sentence means, I need to know which word in the sentence it relates to. I have to consider its context. We can see which word had what contribution to the representation of it, and that it is significantly influenced by other words in the sentence, and most importantly, the thickness of these lines tells me how important a certain word was, and we can see that the animal was correctly identified as the most important word influencing the meaning of it. Another important feature of BERT, which can be seen here, is its bidirectional training. So in many other neural networks for language processing, the meaning of words can only be influenced by previous words. So in this case, only the words above it. BERT, on the other hand, allows words to be influenced by all other words from both directions, and that is actually closer to the way we normally construct our sentences. We can now also have a look at how the influence of other words changes when we alter the sentence slightly to "the animal didn't cross the street because it was too wide." Now, because we changed the sentence, the "it" doesn't mean animal anymore, but it means street. And that means that we can actually see how self-attention adapts the meaning of words depending on their context. And to understand how this can be achieved, we quickly look at the math behind self-attention. This next part is not needed for the comprehension of the rest of this webinar, though. So assume X is the sentence we put into BERT, and each row of X is then one word. So this is the sentence we put in, and each row is one word. And for each word, we calculate something called a query, a key, and a value. And the way this is done is just by multiplying the input with a learned matrix for each of these components. So there's a matrix for a query, there's a matrix for the keys, and there's a learned matrix for the values. I can now multiply the query for each word with the key for all other words, which gives me the importance each word in a sentence has for the meaning of every other word in the sentence. Then there's just some softmax calculation around it, which normalizes the whole expression between 0 and 1, and some normalization factor below here, which is not important at this point. We can also formulate this whole thing as a mathematical formula, and this is what this looks like then. So words can influence the meaning of other words by using this query key value technique, and this is exactly what we call context awareness. And in BERT, self-attention is applied multiple times sequentially on the outputs of a previous self-attention layer, and this allows even more complex relations to be learned than just relations between two words. So now that we have an impression of what BERT looks like, we can see how training for semantic search with BERT actually works. BERT is usually trained in 2 steps, and step 1 is meant to build up a general understanding of language. This step 1 is generally usable, and it does not need to be carried out again for every specific application. This is important because this first step needs lots of computing resources and large amounts of data. And then there's a second step, which is called specialization, and this is different for every specific task. Since the network already has been trained, I need less data and also less computing resources. I need to perform this second step for every specific application I want to use BERT in, though. So let's look at the first step first. And as I said, in this first step, BERT learns linguistic context on 2 different scales. The first scale is based on words, so it It's meant to learn connections between words, and the method used to achieve that is masked language modeling. The way this works is I input a complete sentence into my algorithm, into BERT. In this case, the cat sits in the window, and then I mask out one word, in this case sits, and I let BERT, including an auxiliary layer, predict which word is missing. So in this case, sits. And if I do that with enough sentences, BERT learns to deduce from the context which words are missing. The second step for general linguistic context is something called next sentence prediction, and it is meant to learn connections between sentences. And the way I train BERT for this is I input two sentences into BERT, sentence A and sentence B, and let BERT predict whether A follows B. Simple task. The advantage of this way to learn linguistic context is that I don't need any labeled data. I only need contiguous text for training. And contiguous text is data that is freely available, for example, the Wikipedia or other free corpora. And what is even more important, trained models are freely available. So this whole step can be skipped in your own model development by just downloading the corresponding model, for example, from Hugging Face. Which is, again, very important because this first step is really time-consuming and computationally intensive. The second training step is then meant to optimize BERT for your specific problem, and for this you need problem-specific data sets. How exactly this step looks like is always different depending on the concrete problem you want to solve. In this case, I demonstrated with the example of industry codes, and in order to train in this step, we were provided with a historical collection of business descriptions made by users and the corresponding industry codes. And the way we trained BERT here is we calculated an embedding for a business description done by a user with BERT, and we also calculated embeddings for an industry code and its description provided by the authorities. And then we used a classifier to decide whether business description done by the user and industry code and its description done by the authority match or don't match. And if we do that for all the different industry codes, we can determine which is the best matching industry code for this business description. One advantage of this method is that for production, we can actually pre-calculate the BERT embeddings for all industry codes, because these are static values. We know the industry codes and their descriptions, and we can just calculate their BERT embeddings and save them. So when a user enters its business description in the chatbot, we only need to calculate the BERT embedding of this user business description and can then apply our classifier to determine the top 5 industry codes. This is really nice because we can save computing time by pre-calculating the industry codes, and also this method is theoretically expandable to new industry codes and their descriptions without having to retrain BERT. One caveat here is that pre-calculation is only possible if not too many documents need to be compared. In these cases, there are also alternatives one can use or helper libraries one can use, which are meant for fast similarity search for vectors, for example, FICE or SCAN. One other approach one can take in such a situation is to do a staged procedure. So first do a classical fast machine learning algorithm, and then only sort or rank the top 10 results or top 20 results with a BERT-based architecture. So now that we know how BERT is trained for semantic search, we can look at the concrete project procedure and our results there for industry codes. So in natural language processing, projects usually go through a series of steps, which is rather similar between projects. And the first is always data acquisition and processing. The second is labeling of training and test data. And the third is the evaluation and definition of the machine learning architecture. Labeling of training and test data is grayed out in this case because our client for this project provided us with already labeled data. To be precise, we were provided with 1 million historical business descriptions of citizens and their associated industry codes. And in addition to that, we also downloaded the keywords and continuous text descriptions for all industry codes which are provided by the Federal Statistical Office from Germany, and we used these keywords and continuous text descriptions as additional inputs to calculate our industry code embeddings. We can then train our algorithm on this 1 million or a subset of these 1 million historical business descriptions and their corresponding industry codes. And in order to evaluate our algorithm, we need to choose a target metric. And the choice of such a target metric is always very important because it strongly influences the way we optimize an algorithm. And in this case, users should be shown the 5 most likely industry codes, which means that the best metric to choose here is called recall at X. So meaning if the correct industry code was among the top X results, the assignment is considered correct. And using this metric, so using recall at 5, because we want to show the 5 most likely industry codes, we reached a metric of 0.73 with recall at 5 for BERT, which is pretty good, and it means that in 73% of the cases from our test set, the prediction made by BERT contained the correct industry code among its top 5 predictions. And for comparison to the right, you can see here in grayed out a fast text implementation using only single word embeddings as shown earlier in this presentation, and you can see that it performs way worse. And this hints us on the fact that we probably need context awareness and context understanding in order to interpret users' business descriptions correctly. So now that we have a readily trained algorithm with sufficient performance, we wanted to provide it to a client in an uncomplicated manner. And the way we did it was to provide REST API for a client, and we also designed the algorithm in a way that does not require special hardware. So meaning we only need CPU but no GPU computations, which makes it way cheaper to actually have it in production. Apart from this semantic search on industry code example, there are obviously many other areas of application for BERT and semantic search. And a few examples could be customer communication or product search in e-commerce or interactive FAQs, internal document searches, or information extraction from documents. So to summarize this webinar, we have seen that semantic search is not only used in search engines, but also, for example, for semantic search between documents, and that text search is a trade-off between language comprehension and speed. We can do very fast text search based on exact word matching, which doesn't understand context, or we can use more advanced methods such as BERT, which it understands context very well, but is a bit slower. Connected to that, we've seen that modern AI architectures such as BERT can develop language understanding that goes far beyond finding individual words. It can actually understand context. And the fact that these architectures are available in a pre-trained state makes it very easy to apply modern deep learning, even if I don't have a huge annotated data set, because if you remember, the first step, which is very data intensive of BERT training, is provided freely on a lot of sites. So thank you for your attention, and if you're interested in more webinars by DIDA, you can find videos and slides on our website if you click on dida.do/webinars.